The last lecture, we discussed the LS coupling, and we found that for the lighter atoms, the interaction between spin and orbit interaction, like this, are electrostatic and residual interactions. Electrostatic and residual interactions, like total angular momentum and total spin angular momentum, they individually add, that is J is equal to L plus S, while L is summation of Li for I electrons and S is summation of Si for I electrons. Okay, then it was total J. In that case, we have an unperturbed energy level. We have an unperturbed energy level, and this unperturbed energy level is further splitted due to this spin-spin interaction and electrostatic residual interaction, which is called a residual interaction. Spin-spin will be given by this summation S, and this is given by summation L. And we individually add up them, then we get the total J, total angular momentum. This was LS coupling. And these factors are dominant while the others remain negligible for lighter atoms. In the case of JJ coupling, or in the case of, let me tell you that in the case of higher mass number atoms or atomic number atoms, higher Z atoms, the interaction between spin and orbital angular momentum become important. They become significant. That is, we have here the coupling between spin and orbital angular momentum. That means if we have an electron here and it has an L orbital angular momentum S spin, then J will be L plus S for one electron. For two electrons, it is L1. First we have find, so for one electron, let it be J1. Similarly, for J2, it is L2 plus S2, and for J3, it is L3 plus S3, etc. And then we get the total J1 plus J2 plus J3. This is a simple concept actually. How actually it is done, I will tell you. So the basic concept is that the orbital angular momentum and the spin angular momentum of an individual electron, they are coupled to each other. There is significant interaction between them. So their interactions become important in the heavier atoms because you have the increased number of the nucleons, you have increased number of the electrons. So in this case, we have to treat individually them, and we have to calculate the total angular momentum individually. That is why we take then the total angular momentum J equal to J1, J2, J3. In the earlier case, these contributions were negligible, almost insignificant. They were not of much magnitude as compared to that spin-spin and electrostatic residual interaction. And we know that J is equal to L plus or minus s. The orbital angular momentum quantum number, this j. While as a total j is equal to under root of j into j plus 1 into h dot. This is resultant j. This j is L. So j can be L plus half or it can be L minus half. So j takes only half integral values. J will take half integral values. That means due to spin orbit interaction, the unperturbed energy level is this. So due to spin orbit interaction, this unperturbed energy level, it is splitted into a number of well spaced levels. So there is a definite space between the two levels, and each will correspond to actually a combination of j values for the individual electrons. How many electrons is there? So there's a combination of those electrons, and the smaller j value, smaller j,
सर क्या
lower energy. What I am saying is that, for example, I will give an example. I think you will understand from an example. Let us consider an example of 4p 4d electrons. 4p 4d electron under JJ coupling. First, let us see under LS coupling what will be it. So L1 will be 1, S1 will be equal to 1 by 2. So gives J1 is equal to 1 by 2, 3 by 2. Is it okay? This is for P electron. For D electron, L2 is 2, S2 is again half, gives J2 is again 3 by 2 and 5 by 2. Now there are two electrons. For each electron, there are two possible values of J. So in a system where there are two electrons, which is a two electron system, there is a possible combination of J values. So we have a possible combination of J1, J2 values. And those combinations are given by, it is 1 by 2, 3 by 2. 1 by 2, 3 by 2. Then it is 1 by 2, 5 by 2. Then it is 3 by 2, 3 by 2. And it is 3 by 2, 5 by 2. Okay. So how we treat this two electron system? First, we will try to find out what will be the possible combinations of J values. And we find J by L1 plus S1 to L1 minus S1. That's how we get 1 by 2 and 3 by 2. Similarly, for another electron, we find J2, the combination of J2, or the maximum possible values, minimum to maximum values of J1 and J2, this J2. So again, we go for L2 plus S2 to L2 minus S2. So this is for the simple case of that from LS couplings. Who is writing? If you have any question, you can ask me, because when you write on the screen, so it will disturb everything. So the possible combinations of J1, J2 as a result of spin orbit interaction. So when I say that we are treating JJ coupling, it doesn't mean that LS coupling does not have any role. That has a role, but the magnitude of that interaction is very small as compared to the interaction between spin orbit and this spin orbit interaction as compared to spin orbit interaction. So in general, if I have to draw an energy level diagram for a 4p 4D system, I can go it like this. So this is a 4p before perturbation. Then we have four energy seed, four levels corresponding to each J combination here, 1, 2, 3, 4. So I will take this level 1, 2, 3, 4. This is unperturbed. This is spin orbit interaction. Spin orbit interaction. So the combinations here, this will be 1 by 2, 3 by 2, the lower J values are in lower in energy. This will be 1 by 2, 5 by 2. This will be 3 by 2, 3 by 2. This will be 3 by 2, 5 by 2. This will be when we treat only that spin orbit energy. So we have only the possible J1 and J2 values. This spin orbit energy, what it does actually, it splits this into this four energy levels, and when it splits it into four energy levels, the 1 by 2, 3 by 2 will be lowest energy, and this is of highest energy. Each of
सर
these,
ये हम lowest और highest कैसे बोल सकते हैं?
वो मैं बताऊंगा अभी आपको, आप जस्ट वेट कर लो थोड़ी देर. Now each of these four levels, they will be further perturbed by, you can say that, LS coupling. That means there will be electrostatic, and let me remove this from here. I will draw the energy level here also. So there will be LS coupling. Now you know that how we take the LS coupling. We have J equal to J1 plus J2 to J1 minus J2, or J1 minus J2 to J1 plus J2. So we have 1 by 2, 3 by 2. So this will have two combinations now, 1 by 2 plus 3 by 2 and 1 by 2 minus 3 by 2. This J. So here we will have another energy perturbation, that will be electrostatic and spin energy. Yes, we have energy. Now this will be further separated into two, because our J will have two possible values, that is 1 by 2 plus 3 by 2 and 1 by 2 minus 3 by 2. We are taking the magnitude. So it is 2. This is 1. So 1 will be here, 2 will be here. J values. Similarly, for this level, we have 1 by 2, 5 by 2. This is 3 and 2. So 2 is here. J value. These 2, 3 means these are J equal to J. These are all the J values. for this level, J will be, this is 3 by 2. What is this level? 3 by 2, 3 by 2. So it gives J equal to J1
0 0
minus J2 to J1 plus J2. Okay, J1 minus J2 is
0
0 to 4. So 0, 1, 2, 3, 4. Sorry, 0 to 3 आएगा ये, not 4. We have to take the all possible combinations. So 0, 1, 2, and 3. So here we will have 3 lines. 4 lines, not 3, 4 lines. Oh, I done wrong. Not here. This is here. So J is 0, 1, 2, 3. Similarly for this,
1 to 4
1, 2, 3, 4. So in this is a complete energy level diagram while we treat both the electrostatic spin-spin interaction energy and the spin orbit interactions in this case. So this comes from the JJ coupling. This comes from the LS coupling. So interactions are all possible, but some have higher magnitude. In the case of, like in lower Z, this is higher Z. It is more significant. In lower Z, this will be significant. The difference is only that. But the components will be there. They will be weak there, but they will be there. Now, if you see this, you can have different transitions between these levels, and those transitions will be governed by the selection rules, both in case of this LS coupling as well as in case of JJ coupling. Before that, the general formula for total J will be equal to J1 plus J2 plus J3 minimum, as we have done it in case of that LS coupling, J1 J2 plus 1, but this is minimum. That means we are subtracting actually minus 2 plus. Similarly to J1 plus J2 maximum. This is the maximum. And you can also determine those spectral terms that we will discuss later. I will show you them separately. The selection rules, that means the transitions which are allowed in this configuration here, this configuration. What will be the selection rules for this case? They will be governed by the electric dipole transitions, and we also know that in case of electric dipole transitions, the parity of configuration must change. What does that mean? That means if only one electron makes a transition, that means jumps in the transition. If only one electron jumps in the transition, This is the usual case, as usually. This usually happens. At a time, one electron makes the transition. In this case, in ideal case, actually. Then, for this electron, the electron which makes a transition, for this electron, delta L is equal to plus minus 1. This is also called as Laporte rule. So parity of configuration means that delta L changes from plus 1 or minus 1 by plus 1 or minus 1. So earlier we have delta and L some value, it will change by plus 1 or minus 1 after a transition happened. So that's what the parity of configuration. So earlier it was some 2p1 electron, now it will go to p1 half in p half level. Now it can go to p3 by d or from S to p. So that electronic configuration now changes. And in that case, when one electron jumps, the delta L should be equal to plus minus 1. In some cases, for example, if two electrons jump, then what happens? Then for one electron, delta L1 for one electron, yes, and another electron goes to 0 or plus minus 2. And this rule is same for the case of LS coupling, LS and JJ coupling. I can write it here. Number second point. Delta J is 0 plus minus 1. This was L. This is now J. For jumping electron, which makes a jump or which makes a transition. Delta J should be 0 for all other electrons which are not making any transition. There is no change in J for all other. Third point is for whole atom. That means when we are considering an atom, it goes from some ground state to excited state. That means there is some transition. So in general, for an atom, we can write the total J should be 0 or plus minus 1. But it is important that the transition from J equal to 0 to J equal to 0 is not possible. Is not possible. This is it. Also, delta S is 0, delta L is 0 plus minus 1. And these two transitions in the case of an atom, whole in general atom, is not important. It does not hold. Why? Because we have already included L and S in this case, in J. Because L and S are coupled to each other. And they are also called, they are not good quantum numbers for this case when we take an atom in general as a whole. Then we are already combining L and S to get J. So L and S are also coupled with this J. So we don't need L and S separately. So what is this called is that they are no longer good quantum numbers. They are not good quantum numbers in this case. Now what happens with the energy levels when there is a splitting because of the perturbation? So when there is a split, and what will be the separation between those energy levels which are separated by this perturbation? That means I am talking about what happens. What is going on? Energy interval or spacing between consecutive levels with j and j plus 1 total angular momentum. And there is a simple rule that is called Lande interval rule. This rule is about the spacing between two consecutive energy levels with quantum numbers j and j plus 1. That's total angular momentum, quantum number j and j plus 1 when there is a fine structure. And it states that the energy interval, that is Ej plus 1 minus Ej, that is delta Ej, is proportional to the quantum number j plus 1. This is E here. Ej plus 1 minus Ej is delta Ej, that is directly proportional to j plus 1. It means that the energy interval between for example, if you have this, there is a transition between these two levels. Let me draw it in another form. For example, in this case, let you see this figure. Let me show you this figure. This is a energy level diagram. Now suppose according to selection rules, following the selection rules, there is a transition from this level from this. For example, if there is this transition, okay, the energy level separation between j and j plus 1 consecutive energy levels. Let you remove this. These two levels, let us take these two levels consecutive. This is about the consecutive, that is why I am taking this. So 0 and 1, 1 and 2, 2 and 3, these are consecutive. So energy level separation between 0 and 1 for j equal to 0 and j equal to 1, or for j equal to 1 and j equal to 2, is proportional to the energy of this higher j value or the quantum number. So it is proportional to it is proportional to j plus 1 when you are representing the energy levels in terms of j. The energy interval or the energy spacing between these two lines with quantum number j and j plus 1 is proportional to the higher one, this j plus 1. Simply we will prove this. Let us prove this. Now under LS coupling, if we take LS coupling, the energy of interaction between two energy levels with S and L quantum number it is equal to, I will write some constant, it is L dot S. We have already seen this expressions. Total energy of interaction, that is mu S dot B, and you find an energy term which is L dot S. So there is some constant A. It is the interaction constant. So J equal to L plus S, we all know that. Now J dot J is equal to L square plus, it is mod S square minus plus 2 L dot S, or I can write L dot S is equal to 1 by 2 mod of J square mod of S square. Now therefore delta ES is A by this 2. Here I will write in value of this L dot S. So A by 2, it is J into J plus 1 minus L into L plus 1 minus S into S plus 1 into, there is H cut square by 4 pi here. H square by 4 pi, or H cut square, not H square by 4 pi. H cut square simply. And we have used that J is equal to under root of J into J plus 1 H cut. So therefore we can write delta ES is equal to, I will write A I have incorporated all this A by 2 and this H cut in this A. This is in constant. So I made all the constant terms separate. I separated all the constant terms and represented them by this capital A, uppercase A. In the case of LS coupling, the various energy levels have same values of L and S. So the only thing there remains is A into J plus 1 into J plus 2 in this. So the first factor will be increased by 1, another will remain same, that is J into J plus 1. If you solve it, it is 2A into J plus 1. So what it means? It means that the energy interval that is a spacing between consecutive levels J and J plus 1 of a fine structure multiplet is proportional to J plus 1. That means the larger value of the J, larger of the two of the J values which are involved there. So in case of, for example, we have 3p0. So you understand 3p0, it is P means L is equal to 1 total L for an atom whole, this L, and 2s plus 1 is 3, J is equal to 0. Similarly, if we have another level 3p1, so here J is equal to 1, and for J 3p2, for J is equal to 2. These are the different levels in those atoms where there is a spin orbit interaction, there is an LS coupling. Sorry, the LS coupling, spin orbit interaction becomes for the JJ coupling. So for J equal to 2, they have a separation. You can see that if you take the ratio of these, the ratio of J will be equal to 1:2. That means separation between J equal to 0 and J equal to 1, and the separation between J equal to 1 and J equal to 2. So I can write it like this: J delta Ej, it is 0 1, and delta Ej, it is 0 2 1 2. Sorry. So you can, on this, based on this rule, you can say that what will be the energy level separation. Why this A is a constant, actually that constant we have already derived here in the case of fine structure as well as hyperfine structure, or in case of LS coupling. But in case of JJ coupling, if you treat only JJ coupling for heavier atoms, there exists a deviation in this rule. So there is a deviation in the length interval rule. Okay, now there was one thing that lower J, lower E, and yes, actually this happens in the case when J is half filled, when the orbit is half filled, or more than half filled. And it is lower J, higher E when it is less than half filled. So this is less than half filled, and this is for when it is more than half filled. Actually this J, it is directly related to L plus S, LS coupling. Okay, and if you see Hund's rule, and Hund's rule will apply here. Okay, I will leave here, but go through the Hund's rule 1, 2, and 3.
Okay, sir.
Hund's rule of maximum multiplicity. There are 3 Hund's rules. So Hund's rule 1, Hund's rule 2, and Hund's rule 3. So just see them, and if there's anything remains, we will discuss in next lecture.